Good morning, everyone. Today I will talk about this animal that you see in this picture, which I named it Gary when I was visiting a university in Singapore. And I felt really close to this creature because they told me that it was trying to kind of escape from the aquarium a few times by breaking the glass. So it was it was like an immediate connection, and I named it Gary. What is interesting about this creature is that it's actually one of the top predators. It has in the animal kingdom. It has a really good eye. Basically, it can see with 16 different color receptor, just compared to humans that only have 3 or 4. And not only that, they can actually see polarized light. They can see IR. So you can kind of imagine how colorful their surrounding would be and how they see things around them. But the main thing that is kind of interesting about them is that they have these hammer-like arms. So they actually use this to smash things like what you see in this video, and especially materials that we consider in any textbook as tough, strong materials like seashells, because they actually feed on those creatures like sea snails, crab, and things like that. So they actually use this arm very frequently for hunting and combat. But the interesting thing about them is that what it makes it quite powerful and kind of devastating for these poor snails or mussels is that it punches with a really like a high velocity. So these are some numbers that you can kind of compare to things that you might be familiar with. For instance, that's the speed when like a bullet comes out of a gun, like a 22 caliber. So that's the speed that they punch. And that's the force. So with 1/10 of that force, a normal person can throw a basketball into orbit. Just imagine how powerful it is. And what is interesting is that upon impact, the velocity is so much that through this supercavitation, it actually creates for a fraction of a second temperature close to 2500 centigrade. So that's the temperature for the surface of the sun. And that creates macro bubbles, which when it collapses with the initial impact, it actually together they would work and kind of they would disintegrate the material that they are punching. But then the main question is how they can actually punch so fast. So it has to do with the structure that they have up there on the upper part of their arm. It's a saddle-like shape, and if you have taken calculus in your high school, that's one of those structures that is really stable. I mean, you can compress it. It's really it's really. It can dissipate a lot of energy, so you can imagine that they would basically use muscle to compress and kind of store energy into it, and then they would release it upon need. And the next time that you basically take some Pringles chips, and that's the reason that they have created this shape, because it gives this additional crunchiness, so it tries to resist to the fracture. So that's the thing that comes with that. But then the main question here is that if they are using it that frequently, why themselves they don't break? So that's a key question here. And it's really fascinating. I mean, if you look at the architectural design of this club or the arm, what we see is that it's actually a multi-phase, multi-component nanocomposite. So it's actually made from this chiral nematic superstructure made from chitins, which is a carbohydrate. And then they have kind of reinforced the surface of this chitin with a mineral, hydroxyapatite mineral, that we can actually find it in our bone, in our tooth. So they reinforce the surface with that. And then there's this third component, which is a protein. And this protein actually mediate nucleation and growth of hydroxyapatite. Yeah, sure. I think it doesn't work on the because it's yeah. So essentially, the protein matrix you don't see it in this picture, but because they are in angstrom resolutions and nanoscale, so you don't see it here. But anyway, they would mediate nucleation and growth of hydroxyapatite, but also they act as a reinforcing matrix for this nanocomposite. And the way that the material comes together, like the way that you see here in this colorful manner, it's actually a bilayer architecture that they would form. So they have a really mineral outer shell and that kind of absorb the impact, and then they have this softer interior, which is more blue or violet. That's the way I see it. Probably I'm colorblind, but I mean, yeah. But yeah, I mean, essentially it's much softer, and then this kind of together they would dissipate the energy of the impact. And in this project, we also try to kind of see what else we can find in nature that has this bilayer architecture. So if you have a engineering background, the Ruber's drop is a perfect example where you have this like a core shell type architecture where you have the really stiff outer layer and a softer inner layer, where you can actually shoot at it with 38 caliber in a close proximity and it doesn't break. And then if you are a biologist, or if you are kind of this would be like the closest thing that you can have, having this bilayer architecture where you have this enamel outer layer, which is extremely stiff. It's actually the strongest material or stiffest material in human body. And then it has this dentin layer, which is still mineralized, but the inner part of the human tooth or mammalian tooth, which is still softer, but together they provide this this durability. So in this project, what we try to kind of do, of course, taking inspiration from different components, and then try to see what we can replace those with the things that we have in the lab in more abundant way. And also then try to use synthetic biology toolkit to create some of these building blocks. In this case, basically proteins through this recombinant DNA technology. And what we did, the first thing was to actually replace this chitin superstructure, this kind of chiral nematic shape that they would form. And it was extremely hard to work with chitin. So instead what we used was cellulose nanocrystal. So essentially it's a cellulose that you hydrolyze it with acid, and then you would get these nano whiskers. And what is interesting about CNC is that, we can call it also CNC, is that it actually, if you, in a controlled way, if you remove the water from it, it starts to basically phase separate. And you can actually induce order into this material. So it also forms chiral nematic superstructures in this like twisted way. So we use that. So we basically purchased a bucket of it, and then we just did a lot of tests in the lab to figure out how we can control this. And then the second most important part of this kind of new material that we wanted to make was, of course, the protein. So if you look at the protein that you can find in kind of a natural system, that's the most abundant protein that you can find. It's actually a single protein, but with three functionality. So it has a part that binds to chitin. It has a part that actually mineralizes or kind of control the mineralization of hydroxyapatite, and it has a part that dissipates energy. It's more like a silk-like sequence. And then what we try to do to kind of systematically study this, we try to kind of divide these two, creating one batch of protein that is kind of a reinforcing protein, and the other batch would basically control the mineralization. And we essentially created this like a three-block architecture also. And then we basically mix it with the cellulose nanocrystal. And what is interesting is that when you mix these two together, that you end up having a paste that you can actually mold it. And that's basically what we use to physically kind of use like a CNC machined like an injectable mold for kind of making tooth-shaped structures. And then we actually through really like a extensive processing, which is kind of described in this paper we published last year in Advanced Material, we basically made something that kind of resembles like human tooth, and then we used the second part of this kind of protein design that we had to actually infiltrate this already kind of a nanocomposite form that we made from this reinforcing protein, and then the CNC to actually induce mineralization of hydroxyapatite to actually make a quite similar this bilayer architecture to kind of human tooth. Yeah, with that I would like to finish, because I think, yeah, I went like 1 minute over time, but I think that's acceptable.
Thank you so much.
Yeah.